Astronomers found something they cannot explain. Not a strange signal, not an unusual reading an entire object, 66 billion times the mass of our Sun, sitting in a place in cosmic history where it has no right to be. By every rule we have, it should not exist yet. And the uncomfortable part is not the size. The size is just the symptom. The real problem is the when. Tonight we are going to follow the light from this thing across 10 billion years, and by the end, I think you will understand why the people who study it professionally find it quietly unsettling in a way they struggle to fully articulate. Get comfortable. Subscribe if you have not. This one goes deep. Part 1. This shouldn't be here. Right now, tonight, while you are sitting wherever you are sitting, photons are landing on telescope mirrors perched on the peaks of mountains in Chile, in Hawaii, in the high desert plateaus of New Mexico, and those photons have been traveling for 10.4 billion years to get there. They did not originate from a star. They did not come from a nebula or a galaxy cluster in any ordinary sense. They came from something that, by every rule we thought we understood about how the universe constructs itself, should not exist. And yet here they are, arriving on schedule, carrying information about an object so extreme, so cosmologically inappropriate, that the more carefully astronomers study it, the more uncomfortable the implications become. The object is called TON-618. And before we go any further, I want you to sit with a single fact for a moment, just one, because the way this fact lands matters. TON-618 is a black hole. It has been confirmed as the largest black hole humanity has ever directly characterized. Its mass is approximately 66 billion times the mass of our Sun. Some estimates place it closer to 40 billion solar masses, and even that lower bound does not make the situation any less strange. Either number represents a quantity of compressed matter so extreme that our usual instinct to reach for comparisons starts to fail us before we even begin. We will get to the scale in a moment. But the scale, as extraordinary as it is not actually the problem. The problem is the when. The problem is that TON-618 was already this size, already this massive, already fully formed and blazing across the observable universe, when the universe itself was less than 4 billion years old. And that timing is what breaks the physics. The location, just to orient you in space, is the constellation Canes Venatici, the hunting dogs, a relatively quiet patch of northern sky that you can find trailing behind the handle of the Big Dipper. The distance is 10.4 billion light-years, which means that the light arriving at those telescope mirrors tonight left its source 10.4 billion years ago, before our Sun had ignited, before the Earth had condensed from a protoplanetary disk, before any atom in your body had been arranged by any process into anything that could be called matter with a future. The photons that are arriving right now left TON-618 when the universe was approximately 3.3 billion years old. The universe today is around 13.8 billion years old. So what we are seeing, what those photons are encoding, is a snapshot of an object that existed in the universe's early adolescence, already grown to a size that our models say should have required much, much longer. The discovery, or rather the initial cataloguing, happened the way a lot of profound things in science happen quietly, without any awareness of what was actually being recorded. In 1957, astronomers working at the TON-618 Observatory in Mexico were conducting a photographic survey of the sky. They were doing what sky surveys do, mapping faint objects, assigning catalogue numbers, building the index of what exists up there. Entry number 618 in the TON-618 catalogue was flagged as a faint blue star. That was it, a data point, a routine annotation in a growing ledger of celestial objects. Nobody looked at that entry and thought they had found anything unusual because, from a photographic plate in 1957, TON-618 looked like a star. It had the right color profile, the right apparent magnitude, nothing that screamed extraordinary. The largest confirmed black hole in human history entered our scientific records as a routine data point, filed and forgotten for years. There is something both funny and deeply humbling about that. The universe was not waiting for us to be ready. It just sat there, mislabeled, while we caught up. The reclassification came decades later when spectroscopic analysis revealed the object's true nature. The light was not starlight at all. The spectral lines were stretched, shifted dramatically toward the red end of the spectrum, indicating a recession velocity consistent with cosmological distances. This was not a nearby star. This was a quasar, a quasi-stellar object, meaning an actively feeding black hole so luminous that it outshines everything around it and can be seen across billions of light years. And once you know you are looking at a quasar at that distance, the math begins, and the math is where everything starts to go wrong. Here is the tension, stated as plainly as I can state it. Black holes grow through a process of accretion, meaning they accumulate mass by pulling in surrounding matter over time. That process has a built-in speed limit, a physical ceiling on how fast a black hole can grow, imposed by its own radiation. The details of that ceiling we will get into shortly, but the upshot is this. Starting from the first black holes that could have formed in the early universe, which were the collapsed remnants of the first generation of stars, even under the most optimistic assumptions about continuous feeding and ideal conditions, the mathematics of growth does not produce something the size of TON-618 in the time available. The numbers do not close, not by a small margin, by a significant one. And what makes this more than just an interesting puzzle for specialists is the implication sitting underneath it. If TON-618 exists, and it does, and if our model of how black holes grow is correct, and it might not be, then either the object grew through mechanisms we have not yet identified, or the model is wrong, or the timeline of cosmic history we have been using contains an error we have not yet found. Any one of those possibilities is a significant statement about the state of physics. Taken together, they represent something larger. They represent a genuine crack in the foundation of how we think the universe assembled itself. TON-618 was supposed to be a rare anomaly, a statistical outlier at the extreme tail of the black hole mass distribution, something that existed but that we could mentally quarantine as an exception. It is not an exception. That is what keeps getting worse. But we are getting ahead of ourselves. First, let us try to actually understand what we are dealing with, because the scale of this thing is the kind of scale that, if you let it land properly, quietly reorganizes the way you think about everything else. And if the scale alone does not unsettle you, what comes next absolutely will. Part high scale that breaks intuition. There is a particular kind of number that functions less like information and more like a wall. You read it, you process the digits, you nod, and then nothing actually changes in your mind because the number is simply too far outside anything your brain was built to handle. The mass of TON-618 is one of those numbers, 66 billion solar masses. Your brain reads that and files it somewhere next to very large and moves on. So let us not let it do that. Let us try a different approach, starting not with mass, but with geometry, because geometry is something we can at least attempt to visualize. Every black hole has what is called an event horizon. The event horizon is not a physical surface in any conventional sense. It is a boundary, a threshold, the point in space around a black hole where the escape velocity, meaning the speed you would need to be traveling to break free of the gravitational pull, exceeds the speed of light. Inside the event horizon, nothing escapes. Not matter, not radiation, not information in any form we know how to transmit. It is the point of no return, and its size is directly proportional to the mass of the black hole at its center. The more massive the black hole, the larger the event horizon. For TON-618, the radius of the event horizon, the distance from the center to that boundary, is approximately 1,300 astronomical units. 1 astronomical unit is the average distance from the Earth to the Sun. Pluto, the outermost well-known object in our solar system, orbits at roughly 40 astronomical units from the Sun. The event horizon of TON-618 extends more than 30 times farther out than Pluto's orbit. The diameter, the full width of this boundary from one side to the other, is approximately 2,600 astronomical units. To put that another way, if you placed the Sun at the center of TON-618's event horizon, and you then tried to fly a spacecraft outward at the speed of light in a straight line toward the edge of that boundary, it would take your spacecraft roughly 18 days to reach it. And that is just to reach the boundary. That is not passing through it. That is not escaping. That is simply getting to the edge of the point of no return. And even then you are inside it, because crossing the event horizon going inward happens without any visible marker. There is no wall. There is no flash of light. There is just the horizon, and then the interior, and then the increasingly extreme physics of what happens when space-time curves beyond any comfortable description. Light itself takes approximately 2 weeks to cross the full diameter of TON-618's event horizon. Let that sit for a moment. We are accustomed to thinking of the speed of light as the fastest thing in the universe, 300,000 kilometers per second, fast enough to circle the Earth 7.5 times in a single second, fast enough to travel from the Earth to the Moon in about 1.3 seconds, fast enough to reach the Sun in roughly 8 minutes. And this object's event horizon is so geometrically large that light traveling at full speed takes 2 weeks to cross it. TON-618 is not a point in space. It is a region of space. It is more accurate to think of it as a territory, a domain, a zone where the rules change. And that zone is so enormous that you could stack dozens of solar systems end to end across it and still have room. The comparison to our own galaxy's central black hole is instructive because Sagittarius A star, the supermassive black hole at the center of the Milky Way, is not small by any standard. It masses approximately 4 million solar masses, which is large enough to be the gravitational anchor for a galaxy of several 100 billion stars. TON-618 masses somewhere between 10,000 and 16,000 times more than Sagittarius A star, depending on which estimate you use. If you replaced Sagittarius A star with TON-618, the gravitational consequences for the Milky Way would be immediate and total. The entire structure of our galaxy would reorganize around it. Stars that currently orbit our galactic center in stable elliptical paths over millions of years would be disrupted, accelerated, or consumed. The scale difference between these two objects is not incremental. It is the difference between a boulder and a mountain range. Now, here is something that starts to bend your intuition in an interesting direction. The event horizon is not a surface. It has no texture, no temperature that an infalling observer would detect as they crossed it, no visible line in space. From the outside, looking toward a black hole of this size, what you would see is a sphere of absolute blackness surrounded by a distorted view of everything behind it. The gravitational lensing effect, the bending of light from distant objects by the extreme curvature of space-time around the black hole, would warp the background universe into arcing rings and smeared images. Everything behind TON-618, from our hypothetical viewing position, would be bent around it into a luminous halo. The universe would appear to be wrapping itself around this absence, framing it in curved light like a grotesque optical artifact. Astronomers call that ring of distorted background light an Einstein ring. And for an object as massive as TON-618, that ring would be spectacular, a visual demonstration that space-time in the vicinity of this object is so severely curved that even the geometry of observation itself is compromised. But here is the transition that matters, the one that keeps bringing us back to the central problem. The size is extraordinary, but the size is not what astronomers lose sleep over. The size is a consequence of the mass. The mass is a consequence of the growth, and the growth is the thing that does not fit the timeline. An object of this scale existing at this point in cosmic history is not just a record breaker. It is evidence of a process we have not correctly described. It is a symptom of an incomplete physics. The scale of TON-618 is the footprint of whatever mechanism produced it, and that mechanism is something we are still struggling to name. So, if the size of the boundary alone does not unsettle you, consider what had to happen to produce a boundary that size, in the time that was available, in a universe that was not supposed to allow it. Part Bar. It's not just big, it's alive. A black hole sitting quietly in space, accreting nothing, emitting nothing beyond the theoretical minimum, would be effectively invisible at cosmological distances. You would not detect it. It would simply be a gravitational anomaly, a region of curved space-time, imperceptible from 10 billion light-years away. The reason we can see TON-618 at all, the reason it showed up on a photographic plate in 1957, even if it was mislabeled, is that TON-618 is not quiet. It is feeding, actively, voraciously, at a rate that converts its surroundings into one of the most luminous continuous energy sources in the observable universe. TON-618 is classified as a hyperluminous quasar. The quasar designation tells you it is an active galactic nucleus, meaning the supermassive black hole at the center of a galaxy is actively accreting matter and releasing enormous quantities of energy in the process. The hyperluminous designation tells you it sits at the extreme end of even that already extreme category. Its luminosity is estimated at approximately 140 trillion times the luminosity of the Sun. 140 trillion. Our Sun produces enough energy every second to power human civilization for several 100,000 years. TON-618 produces the equivalent of 140 trillion of those suns, simultaneously, continuously. It outshines thousands of entire galaxies. An average galaxy contains hundreds of billions of stars. TON-618, in terms of raw energy output, makes thousands of those galaxy-scale collections of stars look dim by comparison. The mechanism producing this energy is the accretion disk. Around the event horizon of TON-618, matter, gas, dust, disrupted stellar material, anything that has wandered too close to escape, forms an enormous flattened structure of orbiting material called an accretion disk. As this material spirals inward, several things happen simultaneously. The inner regions of the disk orbit faster than the outer regions, creating shearing forces. Friction between adjacent layers of orbiting material generates heat. Not moderate heat, not stellar core heat. The innermost regions of the accretion disk around a black hole like TON-618 reach temperatures far exceeding the cores of stars, producing radiation across the full electromagnetic spectrum, but with a particularly intense peak in the ultraviolet and X-ray ranges. The gravitational potential energy of infalling matter is being converted, with remarkable efficiency, into electromagnetic radiation. The conversion efficiency of accretion onto a black hole is significantly higher than nuclear fusion, the process that powers stars. A black hole accretion disk is, in terms of energy yield per unit of input mass, one of the most efficient energy conversion processes in nature. Threaded through this accretion disk are intense magnetic fields. The plasma in the disk, ionized matter moving at significant fractions of the speed of light, generates and amplifies magnetic fields as it spirals inward. Those magnetic fields become twisted, concentrated, and under the right conditions they redirect some of the infalling energy outward along the rotational axis of the system, launching what are called relativistic jets. These are narrow beams of plasma and electromagnetic radiation shooting outward from the poles of the black hole at velocities approaching the speed of light extending in some quasars for hundreds of thousands of light years, crossing through and beyond their host galaxies entirely. In TON-618's case, the jets are part of what makes it visible and what originally led to its identification as a radio-loud quasar. These jets carry energy extracted from the accretion process out into the surrounding intergalactic medium, and they are powerful enough to heat and disrupt the gas that would otherwise be available as future fuel for star formation in the host galaxy. Now here is something worth pausing on, because it connects directly back to the central problem. To produce a luminosity of 140 trillion solar luminosities continuously, TON-618 must be consuming matter at an enormous sustained rate. The accretion process that fuels quasars requires a supply of material, and that supply cannot be temporary or intermittent if the quasar is to maintain its observed brightness over extended periods. The light we receive from TON-618 represents a sustained state, not a brief flare, which means that when the universe was just a few billion years old, in TON-618's corner of the cosmos, there was not only already a black hole of 66 billion solar masses, but there was also enough surrounding material, enough raw fuel, enough gas and disrupted matter flowing inward to power continuous hyperluminous emission. Where did that material come from? How did it accumulate so quickly in the early universe? And how, in the time available, did the black hole at the center grow large enough to anchor and drive that process? We do not have clean answers to those questions. We have hypotheses, and we will get to them. But the existence of the quasar activity, the fact that TON-618 is not a dormant relic but an active engine, sharpens the paradox rather than resolving it. A dormant black hole of 66 billion solar masses would be strange enough. An active, feeding, hyperluminous one, burning through matter at a rate consistent with its observed output in a universe less than 4 billion years old, is stranger still. And the strangeness compounds when you start asking how fast it needed to grow to get there. To shine like this, it had to keep eating, consistently, efficiently, without significant interruption, for a very long time. And that brings us to the problem that breaks everything. Part born, the growth ceiling. The universe has speed limits. Some of them are obvious, the speed of light being the most famous. Others are less famous, but just as fundamental, built into the physics of specific processes rather than into the fabric of space-time itself. One of those less famous speed limits governs how fast a black hole can grow by accretion, and it is called the Eddington limit. Understanding this limit is not optional if you want to understand why TON-618 is cosmologically scandalous. It is the wall that the object should not have been able to climb past, at least not in the way our models predict. Here is the conceptual core of it, without the mathematics. When a black hole accretes matter, that matter does not fall silently. As it spirals inward and heats up, it radiates. That radiation, the same radiation that makes a quasar luminous, carries momentum, photons push. Not much, not in everyday experience, but photons exert a pressure on matter they interact with, and in the vicinity of an extremely luminous object, that radiation pressure becomes physically significant. Now picture the situation around an accreting black hole. Gravity is pulling matter inward. Radiation from the accretion disk is pushing matter outward. At some luminosity level, those two forces balance. The outward pressure of radiation exactly counteracts the inward pull of gravity on infalling gas. That balance point is the Eddington limit. If the black hole tries to accrete faster, producing more luminosity, the increased radiation pressure drives away the infalling material before it can be consumed. The accretion process throttles itself. The black hole essentially chokes on its own light. The Eddington limit sets a maximum accretion rate for a given black hole mass, and because the black hole needs to accrete mass to grow, the Eddington limit translates directly into a maximum growth rate. That growth rate is exponential, meaning the black hole can grow proportionally to its own size at each step, which sounds fast. And for a stellar mass black hole, maybe 10 to 20 solar masses, it is fast enough to eventually produce a supermassive object, given enough time. The doubling time under Eddington limited accretion, the time required to double the mass of the black hole, is on the order of tens of millions of years. That sounds short on cosmic timescales, but let us walk through the arithmetic. The first generation of stars in the universe, the population known as population 3 stars, formed somewhere around 100 to 200 million years after the Big Bang. These were enormous, short-lived stars, burning through their fuel rapidly and collapsing into the first black holes. Those first black holes had masses on the order of tens to perhaps a few hundred solar masses. Call it a seed mass of 10 solar masses, which is generous but not unreasonable. From that starting point, growing at the maximum rate permitted by the Eddington limit, how many doublings does it take to reach 66 billion solar masses? The answer is approximately 33 doublings, maybe slightly more. 33 doublings, each taking tens of millions of years, requires a total growth time on the order of 1 to 2 billion years at minimum, and that is under ideal conditions. Continuous feeding at or near the Eddington limit. No interruptions, no feedback effects, no gaps. Here is the problem with that calculation. The light from TON-618 left its source when the universe was approximately 3.3 billion years old. The first black holes could not have formed until at least 100 million years after the Big Bang. That leaves approximately 3.2 billion years of available growth time. The arithmetic is uncomfortable but manageable so far, right? Barely, except that the real universe introduces inefficiencies that the idealized calculation ignores. Accretion is not perfectly efficient. Real black holes do not continuously feed at exactly the Eddington rate. The feedback from quasar activity itself, the radiation and jets we described, heats and disperses the surrounding gas, periodically cutting off the fuel supply. Mergers between galaxies, which also contribute to black hole growth, are not continuously available on demand. And the early universe, while dense and gas-rich in some regions, was not uniformly configured to provide constant fuel to a growing black hole. When you run the growth curve with realistic parameters rather than ideal ones, the required timescale exceeds the available time by a significant margin, not by a factor of 2, which might be explainable by measurement uncertainties or modeling assumptions at the margins, by factors that suggest the discrepancy is real and structural. Both forward calculation, starting from a plausible seed and growing forward in time, and backward calculation, starting from the observed mass and asking what must have happened to produce it, arrive at the same conclusion. Even under the best available conditions, the growth model does not produce TON-618 in the time the universe had. The numbers do not close. And when a physicist says the numbers do not close, they mean one of the assumptions in the calculation is wrong, and the question becomes which one. So we run the timeline backward, and that is where the situation gets genuinely interesting. Part num. Run the clock back. Let us construct the timeline carefully, because the specifics matter here and rushing past them would be doing a disservice to how strange this actually is. The Big Bang, the moment of origin from which we measure cosmic time, occurred approximately 13.8 billion years ago. In the first few 100 million years that followed, the universe cooled from an initial plasma state, protons and electrons combined to form neutral hydrogen, and the cosmos entered what cosmologists call the Dark Ages, a period before stars existed when the universe was filled with gas but no significant sources of light. The first stars, those massive population 3 stars, ignited somewhere around 100 to 200 million years after the Big Bang. Call it 150 million years as a rough midpoint. Those stars burned hot and fast, living for a few million years before collapsing. The first black holes born from those collapsed stars came into existence somewhere around 200 million years after the Big Bang, possibly earlier in some models, possibly somewhat later, but the rough window is the first few 100 million years. Now, the light that left TON-618 and is arriving at our telescopes tonight departed its source approximately 10.4 billion years ago. The universe is approximately 13.8 billion years old. That means the light left when the universe was approximately 3.4 billion years old. At that moment, according to what the photons are telling us, TON-618 was already a fully formed hyperluminous quasar powered by a black hole of tens of billions of solar masses. Working backward from that observation, the black hole must have reached its observed mass at or before the 3.4 billion year mark, which means it had to grow from whatever its seed mass was, formed sometime in the first few 100 million years, to tens of billions of solar masses in somewhere between 3 billion and 3.2 billion years, at the absolute maximum. 3 billion years sounds like a lot of time, but now plot the growth curve, starting from a 10 solar mass seed, growing at the Eddington rate, with a doubling time of approximately 45 million years. 33 doublings takes roughly 1.5 billion years under ideal conditions. So, in principle, the math is tight but perhaps workable, except, as noted, real conditions are not ideal. The accretion efficiency is not 100%. Real quasars, even the most luminous ones, show variability in their emission, suggesting their accretion rates fluctuate rather than remain constant at the Eddington maximum. Episodes of super Eddington accretion, where matter falls in faster than the standard limit would allow, have been proposed and may exist, but they are not guaranteed, and the physics of sustaining them is itself contested. More fundamentally, consider what the seed mass assumption requires. A 10 solar mass seed is already a concession, picking the largest plausible stellar remnant black holes, but the uncertainty is actually larger than that. We do not know with certainty what the mass distribution of population 3 stellar remnants looked like, because we have never directly observed a population 3 star. They are too old, too far, and any that existed have long since died. Our models of them are sophisticated, but ultimately indirect. If the seed masses were smaller than 10 solar masses, which is entirely possible, the growth problem becomes worse, and if the very first black holes were not population 3 remnants at all, if they formed through some other mechanism, then the starting conditions of the entire calculation change. The phrase that keeps coming back in discussions among researchers working on this problem is that the discrepancy is not a rounding error. It is not the kind of tension that gets quietly resolved when someone sharpens a measurement or refines a model parameter at the margins. It is the kind of tension that requires a new ingredient, something that is either not in the current model at all, or something that is in the model but assigned the wrong value at a fundamental level. Either we are missing a mechanism for early black hole growth, or we are missing something about the physics of the early universe that would allow faster growth, or our cosmological timeline contains an assumption that does not match reality. We do not know which assumption used or fails, but we know that something does, and that uncertainty is not a footnote. It is the story. Part Sal, the first crack. When a model produces a result that contradicts an observation, there are a finite number of ways to respond. You can question the observation, you can patch the model, or you can begin asking whether the foundational assumptions underlying the model are correct. The case of TON-618 has, over the years since its quasar nature was confirmed, generated all three responses, and none of them have fully resolved the tension. What has emerged instead is a set of candidate directions, each of which addresses part of the problem, but none of which, in their current form, fully explains what we are looking at. The first direction involves the seed mass. If the initial black holes were much larger than stellar remnants, the growth problem becomes less severe. Rather than starting from 10 solar masses and needing 30 plus doublings, you could start from 10,000 or 100,000 solar masses and need far fewer. This immediately raises its own question, which is, where do such large seeds come from? And the answer most often proposed is direct collapse, not a star forming, living, and dying, but a massive cloud of primordial gas collapsing directly into a black hole without passing through the stellar phase. We will explore that in more detail shortly, but the important point here is that this is a patch to the model, not a confirmation of it. Direct collapse black holes have not been directly observed. They are theoretically motivated and actively searched for, but their existence remains an inference, not a detection. The second direction involves exceeding the Eddington limit. If black holes in the early universe could accrete at rates significantly above the Eddington limit, the growth timeline becomes more forgiving. Super Eddington accretion is not physically forbidden, but it requires specific geometric configurations of the accretion flow that prevent the radiation pressure from dispersing the infalling material. Scenarios involving geometrically thick, optically dense accretion flows, sometimes called slim disks, have been modeled and may permit accretion rates several times the Eddington limit for limited periods. Whether this can be sustained long enough, and whether it was common in the early universe, remains genuinely unresolved. The third direction is the most radical. It questions not the growth rate or the seed size, but the timeline itself. Our cosmological model, the lambda cold dark matter model, makes specific predictions about when structure formed and how fast it grew in the early universe. If those predictions are wrong in ways that allowed structure to form earlier and more rapidly than currently assumed, then the early universe may have provided more fuel, more efficiently, to growing black holes than our standard model describes. This is not a small modification. Adjusting the timeline in the ways required to fully explain objects like TON-618 would require changes to the fundamental parameters of cosmology. That is not a patch. That would be a reconstruction. None of these directions are confirmed. Multiple mechanisms may be required simultaneously, and the deeper implication, the one that connects back to the central question this whole discussion is built around, is that every proposed fix shares a common acknowledgement. TON-618 exists in a state that our current physics, applied honestly to the available timeline, does not naturally produce. Every fix is an admission that something in our understanding of early cosmic history is incomplete. The crack is real. The question is how deep it goes. Part by skipping stars entirely. Among the candidate mechanisms for explaining the existence of objects like TON-618, the one that has attracted the most sustained theoretical attention, is a scenario that sounds almost like science fiction until you look at the conditions in the early universe and realize it might be entirely natural. The idea is called direct collapse, and it proposes that in certain very specific regions of the early cosmos, enormous clouds of primordial gas could bypass the star-forming process entirely and collapse directly into a black hole of enormous mass. The normal route from a gas cloud to a black hole runs through a star. Gas collapses under gravity, heats up, ignites nuclear fusion, burns for millions to billions of years depending on mass, and eventually exhausts its fuel and collapses. The remnant, if the star is massive enough, is a black hole. But this process fragments the gas cloud. As it cools and collapses, different regions reach the density threshold for star formation at different times, and the cloud breaks apart into many smaller objects rather than collapsing as a single unit. To get around this fragmentation and collapse a gas cloud directly into a single massive object, you need to prevent the cloud from cooling efficiently. Cooling is what enables fragmentation. If you can keep the gas warm, you suppress the fragmentation, and the collapse proceeds as a whole. In the early universe, before the first generations of stars had produced heavy elements, the chemistry of cooling was simpler and more constrained. Primordial gas consisted almost entirely of hydrogen and helium, with no carbon, no oxygen, no metals to act as efficient cooling agents. Under these low metallicity conditions, the primary cooling mechanism was molecular hydrogen, and if you could dissociate that molecular hydrogen using an external radiation field, you could keep a gas cloud from cooling effectively. The candidate radiation source for this dissociation is the ultraviolet light from nearby star-forming regions. In a cosmological environment where a massive star-forming galaxy sits close enough to a collapsing gas cloud to bathe it in dissociating radiation, the conditions for direct collapse might be met. The gas cloud cannot fragment efficiently. It cannot form stars. It collapses as a single mass, directly, into what theorists call a direct collapse black hole, or DCBH. The mass of the resulting object could be in the range of 10,000 to 100,000 solar masses. That is a starting seed dramatically larger than any stellar remnant, and a larger seed means fewer doublings required, which means a shorter growth time needed to reach the observed masses of objects like TON-618. The growth problem does not disappear entirely with direct collapse seeds, but it becomes significantly less severe. The timeline becomes at least plausibly workable, whereas with stellar mass seeds, it is difficult to make it work at all. The problem is that direct collapse requires a very specific conjunction of conditions: low metallicity, a nearby but not too nearby ultraviolet radiation source, and the right gas mass and density. Estimates of how commonly these conditions align in the early universe vary considerably, and the concern is that the conditions may be rare enough that direct collapse black holes, while real, do not form in sufficient numbers to account for all the supermassive black holes we observe. In particular, explaining something at the extreme end of the distribution, like TON-618, may require either an exceptionally large direct collapse event or a direct collapse seed that then grows with unusual efficiency, or some additional mechanism on top of direct collapse. The best theoretical candidate for early massive black hole seeds still struggles to fully explain the most extreme object we have found, which is itself a statement about how far outside the expected distribution TON-618 sits. Part Tarm, Chaos Builds Giants. There is a second candidate mechanism that approaches the problem from a completely different angle, and it invokes the violence of the early universe rather than the chemistry of it. The idea is that, in the extremely dense stellar environments that existed in early galaxies, stars did not simply form and evolve in isolation. They formed in enormous, tightly packed clusters, and in those clusters the densities were so extreme that stellar collisions were not rare events. They were common ones. And what happens when stars collide repeatedly in a crowded environment is something that could, under the right circumstances, produce black hole seeds of significant mass through a process that bypasses the normal stellar evolution timeline entirely. The scenario works roughly as follows. A dense cluster of massive early stars forms. The stars are packed closely enough that within a relatively short period, measured in millions rather than billions of years, runaway stellar collisions begin. Massive stars, which have strong gravitational fields and large physical cross-sections for collision, merge with each other repeatedly. Each merger produces a more massive object. That massive object has an even stronger gravitational field, making subsequent mergers more probable. The process accelerates, producing what is sometimes called a runaway merger scenario, where one object in the cluster accretes an increasing fraction of the cluster's total stellar mass through repeated collisions rather than through accretion of diffuse gas. This object, growing rapidly through direct stellar mergers, eventually becomes massive enough to collapse into what is called an intermediate mass black hole, with a mass that could range from hundreds to tens of thousands of solar masses, significantly larger than any individual stellar remnant. Once you have an intermediate mass black hole formed this way, It can then begin accreting the remaining gas in its environment and potentially merge with other black holes, continuing the mass accumulation through both gas accretion and direct mergers. In dense early galaxy environments, where multiple such clusters might form in close proximity, their central black holes could merge as the clusters themselves merge, combining their masses and creating larger seeds for the next stage of growth. The attraction of this scenario is that it does not require any new physics beyond what we already observe in dense stellar clusters today, just applied in a more extreme early universe context. The early universe was denser, its first galaxies were more compact, and the conditions for runaway stellar collisions may have been more commonly met than they are in the modern universe. The challenge is timescales and densities. For the runaway merger scenario to produce seeds large enough to contribute meaningfully to objects like TON-618, the clusters need to be extremely dense, denser than typical modern globular clusters, and the collision and merger process needs to proceed quickly enough to not be disrupted by the feedback effects of the massive stars themselves, which shine intensely and blow away their surrounding material before dying. Whether the earliest universe provided conditions extreme enough to make this scenario efficient is an open question. What it does suggest, and this is relevant to the central story, is that if this mechanism operated broadly in the early universe, it implies an early cosmic environment that was significantly more chaotic, more dynamic, and more violent than our standard models depict. The universe would not have been gently building its first structures in an orderly progression. It would have been crashing things together rapidly, violently, and producing objects that our orderly models struggle to account for. Part Gene born before everything. The third candidate mechanism is the strangest one, and it is also the one that, if correct, would require the most significant revision to our understanding of cosmic history. It involves the possibility that some black holes in the universe did not form from the collapse of stars at all, not from direct collapse of gas clouds, not from stellar mergers in dense clusters, from the very early universe itself, from the dynamics of the Big Bang and the moments immediately following it, before the first stars, before the first atoms, before the conditions for any of the other mechanisms existed. These hypothetical objects are called primordial black holes. The idea, first proposed in the 1970s by Stephen Hawking and others, is that in the extreme density fluctuations of the very early universe, regions of space that were slightly denser than average could have collapsed under their own gravity before the universe had time to smooth those fluctuations out. The density variations required are larger than the typical quantum fluctuations that seeded galaxy formation, but within the theoretical range of what certain inflationary models predict. If such collapses occurred, they would have produced black holes during the first fractions of a second after the Big Bang, with masses that depend on the size of the density fluctuation and the moment of collapse. Crucially, primordial black holes could, depending on the formation scenario, start with masses far larger than any stellar remnant, potentially even in the range of thousands or millions of solar masses, bypassing the growth problem entirely. The radical implication of primordial black holes as seeds for supermassive objects like TON-618 is that they would not have needed to grow to their masses. They would have begun close to those masses, or at masses that required only modest growth to reach them, and the entire timeline problem dissolves. TON-618, in this framing, would not be the product of 3+ billion years of careful mass accumulation. It would be the direct descendant of a primordial density fluctuation, a relic of physics that operated in the first moments after the Big Bang, before the universe had formed anything we would recognize as matter in the conventional sense. The problem with primordial black holes, as an explanation for TON-618, is that there is no direct observational confirmation of their existence. There are indirect constraints, cosmological observations that set limits on how many primordial black holes could exist in various mass ranges without producing detectable effects. and some of those constraints are tight. There are also hints, occasionally discussed in the literature, that certain gravitational wave signals or microlensing detections might be consistent with primordial black holes, but none of these hints has solidified into a confirmed detection. Primordial black holes remain a theoretical possibility, actively researched and taken seriously, but not yet observed. If they exist, and if they served as seeds for objects like TON-618, then the entire timeline of black hole formation predates stars, predates galaxies, predates everything we normally think of as cosmic structure. The black holes would have come first, and everything else built itself around them. That would mean our cosmic history is not just incomplete at the edges, it would be incomplete at the very beginning. Part MUI enter the James Webb Space Telescope. For decades, the observational constraints on early universe black holes came primarily from ground-based telescopes and from space observatories like the Hubble Space Telescope, each of which had hard limits on how far back in time they could peer and what they could resolve at extreme distances. The Hubble, launched in 1990, was transformative for our understanding of galaxy evolution and cosmic history, but its optical and near-infrared sensitivity had a practical ceiling. The light from objects at the highest redshifts, the objects in the most distant and therefore earliest universe, is stretched so far toward the infrared by cosmic expansion that Hubble simply could not detect it efficiently. The theoretical problems with early black holes were known, but the observational data available to test competing models was limited. That changed in December 2021, when the James Webb Space Telescope launched from the Guyana Space Center in French Guiana, and it changed in a way that nobody was fully prepared for. JWST was designed to see the infrared universe with unprecedented sensitivity and resolution. Its primary mirror, 6.5 meters across, composed of 18 gold-coated beryllium segments, was constructed specifically to collect the long-wavelength light that carries information about the earliest epochs of cosmic history. The telescope operates at cryogenic temperatures, shielded from the sun by a tennis court-sized sun shield, and it was positioned at the second Lagrange point, a gravitationally stable location approximately 1.5 million kilometers from Earth. From that position, looking out toward the distant universe, it began seeing things that produced, in many cosmologists, a reaction best described as quiet alarm. The alarm was not about any single observation, it was about a pattern. JWST began detecting massive galaxies at redshifts corresponding to times when the universe was less than 1 billion years old. Not small, young, primitive proto-galaxies still assembling their first stars. Mature, structured galaxies with significant stellar masses, galaxies that our models said should not have had enough time to assemble that much stellar material. And accompanying many of these unexpectedly mature galaxies were signatures of active galactic nuclei, meaning actively feeding central black holes, already massive, already powerful, at cosmic epochs where our models said such objects should still be in their infancy. The significance of this cannot be overstated. It is the difference between finding a single anomalous object, which TON-618 had long represented, and finding a pattern. TON-618, for all its extremity, could be dismissed, mentally at least, as a statistical outlier, an extreme edge case that the standard model could in principle accommodate if the conditions happened to be just right. When JWST started showing not one such anomaly but a population of them, with massive black holes appearing in the first billion years of cosmic history across multiple lines of sight and multiple observational programs, the dismissal became harder. The data was not pointing at an exception, it was pointing at a systematic discrepancy between what the standard model predicted and what the universe actually produced. TON-618 had been a warning. JWST confirmed that the warning deserved to be taken seriously, and then astronomers started seeing them everywhere. Part Muimort, the little red dots. Among the most striking and unexpected findings from early JWST observing programs was the discovery of a population of objects that quickly acquired an informal name in the astronomical community, the little red dots. These are compact, faint sources detected at high redshifts corresponding to the early universe, characterized by a distinctive reddish color in JWST's infrared imaging. They were not red because they were cool. They were red because their light had been stretched toward longer wavelengths by the expansion of space, shifted from the ultraviolet and optical into the infrared as it traveled across billions of light years to reach us. The compactness, meaning how concentrated their light appeared in JWST's imaging, was unexpected, and the numbers were unexpected. Early estimates suggested they were far more common in the early universe than standard models had predicted. Spectroscopic follow-up of some of these little red dots, the process of spreading their light into its component wavelengths to identify chemical signatures and measure precise distances, revealed something provocative. Many of them appear to be active galactic nuclei, actively feeding black holes, and not small ones. The black holes inferred from the spectroscopic signatures of some little red dots are, in some cases, surprisingly massive for their cosmic epoch, appearing within the first billion years of the universe's history, with masses that strain the same growth timelines that TON-618 had already pushed to their limits. The population of little red dots is still being characterized. The data is recent, the analysis is ongoing, and the interpretations are actively contested within the community. Some researchers have proposed that they might represent a mode of black hole growth or a phase of galaxy evolution that is genuinely absent from current models. Others argue that selection effects, biases in which objects are detectable and which are not, might be partially responsible for the apparent overabundance. Still others suggest that some of the apparent little red dots might be compact star-forming galaxies rather than active black holes, though the spectroscopic evidence for AGN activity in many of them is difficult to dismiss. What is not seriously in dispute is that JWST has found objects in the early universe that were not predicted in the numbers or at the masses that are being observed, and that the little red dots represent a population whose existence requires explanation. The connection back to TON-618 is direct. TON-618 sits at the extreme end of the mass distribution of supermassive black holes, the largest known example of a broader population. The little red dots, if confirmed as early active black holes, suggest that population extended back into the first billion years of cosmic history in numbers that standard formation models do not account for. TON-618 is the most extreme known data point in a distribution whose shape and extent we are only now beginning to map accurately, and JWST is showing that distribution is larger and forms earlier than we thought. The anomaly is not shrinking as we get more data. It is multiplying. Part Muihai from anomaly to pattern. There is a specific moment in the scientific process that is different in kind from anything that comes before it. It is the moment when an anomaly, a single strange observation that you have been trying to explain away or isolate as an exception, is revealed to be a pattern. That moment is uncomfortable in a productive way. An anomaly invites you to patch your model. A pattern invites you to question it. The accumulation of JWST data over its first years of operation brought cosmologists and black hole astrophysicists to that second, more uncomfortable moment. It was not just the little red dots. It was the combination of multiple independent lines of evidence all pointing in the same direction. The unexpectedly massive early galaxies, the overly luminous quasars at high redshift, the compact red AGN candidates, the spectroscopic confirmations of black hole masses in the early universe that exceeded model predictions. Each individual finding could be challenged, its methodology questioned, its interpretation contested. but the convergence of multiple independent findings, discovered by different teams using different instruments and different analysis approaches, all arriving at the same broad conclusion, was harder to dismiss. The conclusion was that the standard model of structure formation, the lambda-cold dark matter, cosmology that has been the working framework of modern cosmology since the 1990s, and that has accumulated extraordinary observational support across a wide range of phenomena, makes predictions about the early universe that appear to be incorrect. Not wrong in their general character, not wrong about the existence of structures and their hierarchical assembly, but wrong in a specific and important way. It predicts that the massive end of the galaxy and black hole mass distribution should build up slowly, with the most massive objects appearing relatively late in cosmic history. What JWST is seeing instead is that the massive end of the distribution was populated earlier, more completely, and with objects of greater mass than predicted. We did not find an exception. We found a rule we do not understand, and that rule is one that TON-618, sitting at the extreme end of the entire known distribution, had been pointing us toward for years. To say that the standard model is wrong is not quite the right framing, because the standard model has not been discarded. It is better to say that it appears incomplete in a specific regime, the very early universe at the highest densities and the earliest formation epochs. Whether this incompleteness requires minor modifications, the addition of new mechanisms like direct collapse or primordial black holes within the existing framework, or whether it requires more fundamental revisions, is an open question that the community is actively debating. What is not in question is that the data from JWST has shifted that debate from theoretical speculation to observational urgency. The question of how objects like TON-618 formed is no longer a curiosity at the margins of cosmology. It is a central, unresolved problem, and the data keeps arriving, week after week, from a telescope 1.5 million kilometers from Earth, and every new image makes the problem a little harder to ignore. Part Muibar, the misleading fear. Before we go any further, there is something in the title of this discussion that deserves a direct and honest address, because it is the kind of claim that can generate a specific type of anxiety if left unchallenged. The suggestion that TON-618 is coming for us, arriving, approaching, requires a brief grounding in cosmological geometry, because the reality of the situation is actually both more reassuring and more interesting than the alarming framing implies. TON-618 is not moving toward us. To the extent that it has a motion relative to us, it is moving away from us, carried by the expansion of space along with every other distant object in the universe. The cosmological expansion that stretches the light from TON-618 toward the red end of the spectrum as it travels toward us is the same expansion that is increasing the distance between us and every sufficiently distant cosmic object. At 10.4 billion light-years, TON-618 sits far beyond the scale at which individual gravitational interactions with our galaxy could produce any relevant effect. There is no collision trajectory, no approach vector, no threat of contact on any timescale that has any meaning for human experience or even for the lifespan of our solar system. Whatever TON-618 is doing at this moment in its own cosmic neighborhood, it has no bearing on anything in ours. You can exhale, but here is where the reframe matters, the one that connects this moment of reassurance directly back to everything this conversation has actually been about. The real thing arriving from TON-618 is not the black hole itself. It is information, photons, the electromagnetic record of conditions in the early universe, encoded in the light that left that object 10.4 billion years ago and has been traveling through expanding space ever since, passing through cosmic structures, being lensed by intervening matter, stretched by expansion, and finally arriving at telescope mirrors on Earth, where it is being converted into data that challenges our models of how the universe works. The physical object poses no threat, But the information the photons carry is, in a sense, more destabilizing, because the message they bring is that our understanding of cosmic history is incomplete in ways we are only beginning to measure. Part Muy Born the Real Arrival. So let us pivot to what is actually happening every night on those mountain peaks, because I think this part of the story deserves more time than it usually gets. On the peaks of Mauna Kea in Hawaii, at an elevation of about 4,200 meters, where the air is thin enough that technicians need to acclimatize before working long shifts, telescopes the size of buildings are pointed at a patch of sky in the northern constellation Canes Venatici. In the Atacama Desert of Chile, one of the driest places on the surface of the Earth, where the lack of atmospheric moisture makes the sky almost preternaturally clear, more instruments are doing the same thing. At the Roque de los Muchachos Observatory on the island of La Palma in the Canary Islands, perched above a sea of clouds at 2,400 meters, the same quiet work is happening. Telescopes are collecting light. That seems like a mundane statement until you think carefully about what light actually is, and where this particular light has been, and what it has passed through to get here. Light is not a passive medium. It is a carrier of information, and it is arguably the most faithful information carrier that the universe provides. Each photon, each individual quantum of electromagnetic radiation, encodes in its wavelength and in its polarization and in its arrival direction the physical conditions of the object and environment from which it originated. When photons leave an accretion disk, they carry with them a record of the temperature of that disk at the moment of emission. They carry information about the composition of the material, the specific chemical and ionic signatures of whatever elements were present in the plasma. They carry, embedded in their frequency, information about the velocity of the emitting material, because plasma moving toward us compresses the wavelength of emitted light slightly, and plasma moving away stretches it. And this Doppler signature tells us how fast the material was moving and in what direction. The strength of the magnetic fields threading through the accretion disk leaves an imprint on the polarization of the emitted photons. The mass of the black hole driving the entire process shapes the overall structure of the emission spectrum. All of this information is embedded in the photon at the moment of its creation, in the superheated plasma of the accretion disk around TON-618, and it is carried faithfully across whatever distance the photon subsequently travels. The journey modifies the photon in specific, measurable ways, the stretching of its wavelength by cosmic expansion, the bending of its path by gravitational lensing as it passes near massive structures, the occasional scattering or absorption by intervening matter. But the information is not lost. It arrives. It lands on the mirror. It becomes a number in a dataset. And from that number and thousands of others like it, astronomers reconstruct what the source looked like 10.4 billion years ago. The photons from TON-618 that are arriving tonight left their source 10.4 billion years ago. Let us be precise about what that means in terms of cosmic history, because the numbers are abstract until you anchor them to something. At the moment those photons were emitted, our sun did not exist. It would not form for another 6 billion years. The molecular cloud from which the sun would eventually condense, a loose aggregation of gas and dust in what would become an outer spiral arm of the Milky Way, had not yet assembled itself into anything coherent. The atoms that currently make up the sun, the earth, the oceans, the atmosphere, and every human being alive on the planet right now were scattered across different regions of a galaxy that was still in an earlier phase of its own evolution, dispersed as stellar remnants and interstellar gas from earlier generations of stars, not yet collected, not yet processed, not yet organized into anything with a future. You are younger than the light you are seeing when you look at TON-618, significantly younger, not by a generation or a geological era, by billions of years. Every atom in your body is younger than those photons. The photons have been traveling since a time when your atoms had not yet been organized into anything at all, had not yet been forged in the nuclear furnace of a star, had not yet been scattered by a supernova explosion into the interstellar medium from which the sun's protoplanetary disk would eventually condense. The photons predate you at the atomic level. They predate the raw materials of you. And those photons did not travel through empty, static space. They traveled through a universe that was actively, dramatically evolving around them during every moment of their journey. When those photons began their trip, the universe was 3.4 billion years old, and it contained structures that were young by any cosmological measure. Galaxies were still assembling their primary stellar populations. The large-scale cosmic web of filaments and voids was still taking shape. The first rocky planets were only beginning to form around the earliest generations of sun-like stars. During the 10.4 billion years that followed, while those photons were in transit, moving through space at the speed of light, and yet still taking 10 billion years to cross the distance, the universe built the majority of the stars that currently exist. It assembled most of its galaxies into the large-scale structures we spend careers mapping today. It formed the first generation of Earth-like planets around sun-like stars. On at least one of those planets, and possibly on others we have not yet found, it saw the chemistry of simple molecules organize itself over billions of years of patient trial and error into the chemistry of self-replicating systems, and those self-replicating systems into multicellular life, and that life into nervous systems, and those nervous systems into consciousness, and that consciousness into curiosity, and that curiosity into telescopes. The photons arrived, finally, at a species that had only recently figured out that the faint smudges in the night sky were entire galaxies of hundreds of billions of stars. They arrived at a species that had only within the last century determined that the universe was expanding, that it had a beginning, that its age could be measured. Those telescopes were pointed at the right patch of sky at the right moment, and the photons landed on mirrors made of polished glass and aluminum and silicon, and were focused by precision optics into spectrographs, and were converted by charge-coupled devices into electrical signals, and those signals were digitized and recorded and transmitted to servers, and examined by researchers who had spent years or decades developing the tools to interpret what they were looking at. A transmission sent 10.4 billion years ago, composed in the physics of an accretion disk around a black hole that should not have existed, was received in the 21st century by beings who were not yet a part of the universe when it was dispatched, not even close to being a part of it. The universe was more than 2/3 of its current age before anything capable of receiving the message existed anywhere we know of. That is what is arriving on those mountain peaks tonight. Not a threat, not a danger, a message. An extraordinarily old, extraordinarily well-travelled piece of information about the conditions of the early universe, delivered by the most reliable courier in existence, at the only speed the universe permits for such deliveries, and the message keeps arriving. Every clear night, every time a telescope somewhere on this planet collects another photon from that ancient source, the transmission continues. It has been arriving since before we had the instruments to detect it. It will keep arriving long after we have refined those instruments into forms we cannot yet imagine. The universe dispatched this message before the Earth existed, and it is still sending it photon by photon, continuously, patient in a way that only physics can be patient. The question, the one that makes all of this matter, is what the message actually says, and what we are supposed to do with the answer once we have it. And the answer, it turns out, is considerably stranger than anyone expected. Part Muilam, the 10 billion year transmission. Follow a single photon, not as a metaphor, not as a thought experiment designed to make a point and then be discarded, but as a genuine narrative, because the journey of a photon from TON-618 to a telescope mirror on Earth is one of the most extraordinary itineraries that anything in the observable universe can take, and following it carefully, step by step, reveals something fundamental about the nature of what astronomy actually is and what we are really doing when we point instruments at the sky. The photon originates in the accretion disk of TON-618, and already, at the moment of its creation, the local conditions are so extreme that describing them in ordinary language requires a series of escalating comparisons that still fall short. The accretion disk is a flattened structure of infalling plasma, gas, and disrupted matter spiraling inward toward the event horizon under the gravitational influence of a black hole massing tens of billions of times the Sun. Within that disk, particularly in the inner regions closest to the event horizon, temperatures reach into the millions of degrees, not the thousands of degrees at the surface of a star. Millions. The plasma in those inner regions is moving at velocities that are a significant fraction of the speed of light, and the friction between adjacent layers of this differentially rotating material generates energy on a scale that makes stellar fusion look modest by comparison. Magnetic fields of enormous strength thread through the entire structure, twisted and amplified by the motion of the conducting plasma, occasionally snapping and reconnecting in events that release concentrated bursts of additional energy. In these conditions, photons are generated continuously, absorbed, scattered, re-emitted, generated again, in a dense, rapid cycle within the optically thick inner regions of the disk, where the plasma is too dense to allow easy escape. Our photon, eventually, makes it out. The path from creation to escape is not a straight line. It is a chaotic random walk through a medium that is simultaneously generating it, absorbing it, and scattering it in all directions. But statistical chance eventually places our photon on a trajectory that carries it outward, through progressively less dense layers of the disk, through the somewhat more transparent outer regions of the quasar's surrounding material, past the broader envelope of gas and dust associated with the host galaxy of TON-618, and finally into the intergalactic medium, into open space, into the beginning of its journey. The entire escape process, from creation in the inner disk to clearance into free space, may take thousands of years despite the photon's extraordinary speed, because the medium it is navigating is so dense. But eventually it clears, and then it travels. At the moment of escape, the photon's wavelength places it in the ultraviolet range of the electromagnetic spectrum, consistent with the emission characteristics of plasma at the temperatures present in the inner accretion disk. It is carrying in its wavelength, its polarization, and its direction of travel a precise record of the conditions in which it was created. The universe it is entering at this moment, 3.4 billion years after the Big Bang, is not the universe you are sitting in now. It is a younger universe, and in important ways, a different one. Galaxies at this epoch are generally more compact, their stellar populations younger and more actively forming, their gas supplies less depleted by billions of years of star formation. The large-scale structure of the cosmic web, the network of filaments and sheets and voids that organizes matter on the largest scales, exists but is less fully developed than it will eventually become. The universe has had 3.4 billion years to build itself, and it has accomplished a great deal in that time, but it has not finished, and it will not finish for billions of years more. Our photon does not observe any of this. It simply travels, at the only speed it knows, in the direction it was emitted. 1 million years pass. The photon is still traveling. The host galaxy of TON-618, the structure it escaped from, is now 1 million light-years behind it, and from that distance it would appear as a blazing point of light, the quasar outshining everything around it. The photon does not look back. 100 million years pass. The universe around the photon is evolving continuously. Stars are forming and dying. Galaxies are merging and separating. The large-scale filamentary structure, is becoming more pronounced as gravity draws matter along the cosmic web toward nodes of concentration. The photon passes through regions where this structure is assembling, threading between the filaments and voids of the intergalactic medium, interacting with essentially nothing, because the intergalactic medium, despite containing matter, is so extraordinarily diffuse that a photon can travel for billions of light years without encountering anything that absorbs or deflects it significantly. Meanwhile, something important is happening to the photon itself, something it has no choice about and no awareness of. Space is expanding. The universe is not static. The distance between any 2 points not held together by local gravity is increasing, and as the fabric of space stretches, the wavelength of any photon traveling through it stretches proportionally. Our photon began its journey as an ultraviolet photon. After a few billion years of travel through expanding space, its wavelength has been stretched into the optical range, the range of light that human eyes can detect. It has not lost energy in any conventional sense. Space itself has redistributed its energy across a longer wavelength. By the time the photon has been traveling for 8 or 9 billion years, its wavelength has been stretched further still, into the near-infrared, the range of light that human eyes cannot see, but that infrared-sensitive detectors can detect readily. The photon has been cosmologically redshifted, and that redshift is itself information, encoding in the photon's current wavelength the record of how much space has expanded since the photon was emitted, which tells astronomers precisely how far away and how long ago the source existed. The photon passes through a region of intergalactic space where a massive galaxy cluster sits, hundreds of galaxies bound together by their mutual gravity into a structure massing hundreds of trillions of solar masses. The photon does not hit anything in the cluster, but it passes close enough that the curvature of space-time around the cluster bends its path slightly. Not dramatically, but measurably. This gravitational lensing leaves a small but real deflection in the photon's trajectory, a record of the mass distribution it passed near, added on top of all the other information it already carries. The photon adjusts its path by a tiny fraction of a degree and continues. It enters the local group of galaxies, the small cluster of dozens of galaxies of which the Milky Way and Andromeda are the largest members. It approaches the Milky Way itself, the galaxy that the beings who will eventually detect it call home. It crosses the outer halo of the Milky Way, a sparse region of old stars and diffuse gas extending hundreds of thousands of light-years from the galactic center. It threads inward through the spiral structure of the disk, passing between stars that are completely unaware of its existence, crossing regions of gas and dust that could, in principle, absorb it, but through statistical fortune do not. It crosses the orbital path of the solar system, the ring traced out by 8 planets and countless smaller bodies around a middle-aged yellow star, and the solar system is occupied and inhabited and full of radio signals and artificial satellites, none of which the photon interacts with at all. It enters Earth's atmosphere. Here, for the first time in 10.4 billion years of travel, the photon begins to experience real resistance. The atmosphere is not the vacuum of intergalactic space. It has density gradients, temperature variations, pockets of turbulence, layers of composition. The photon is refracted slightly as it descends through these gradients, its path bent by the changing refractive index of the air, the same basic optical effect that makes a straw appear bent in a glass of water, but happening on a scale that matters for precision, astronomy, and that engineers have spent enormous effort learning to correct for. The photon reaches the dome of the telescope. It enters through the open aperture. It strikes the primary mirror. The primary mirror is a surface of polished glass coated with a thin layer of aluminum or silver, shaped with extraordinary precision into a parabolic curve that focuses incoming light to a point. The photon is absorbed by an electron in that metallic coating. The electron is excited to a higher energy state. The photon, as a photon, ceases to exist. its energy has been transferred. The excited electron relaxes, and the energy cascades through the detection system, eventually producing a tiny electrical signal in a charge-coupled device at the telescope's focal plane. That signal is amplified. It is converted to a digital value. It is recorded to a storage medium. The photon has become a number, one entry in a spectrum, one data point in a data set that will be combined with millions of other such measurements from other photons that made the same journey to produce a measurement of the redshift, luminosity, and spectral characteristics of TON-618. 10.4 billion years of travel, an origin in conditions of physics so extreme that our language strains to describe them. A journey through a universe that assembled itself, built its stars and galaxies and planets, and eventually its observers, while the photon was in transit, and it ends as a single row in a table, examined by a researcher on a computer screen who looks at the numbers and realizes that they do not fit the model. That single data point, carried across 10.4 billion years by a single photon born in the accretion disk of an object that should not exist, is evidence. Quiet, precise, irrefutable evidence. And what it is evidence of is that we do not yet fully understand how the universe we are sitting inside actually assembled itself. The photon traveled 10 billion years to deliver that message. The least we can do is take it seriously. Part Sao, the model is incomplete. We have arrived finally at the place this entire discussion has been building toward, not with a dramatic reveal, because science rarely works that way, and anyone who has spent time around working scientists knows that the actual moments of recognition are quieter and more gradual than the popular narrative of discovery tends to suggest. What we have instead is an accumulation of evidence, assembled over decades, sharpened by each new instrument and each new observation, that has brought us to a clear and genuinely uncomfortable assessment of where things stand. The standard cosmological model, the framework that has guided our understanding of the universe's structure and history for the past several decades, makes specific, testable predictions about how and when the most massive objects in the universe should form. Those predictions are in tension with what we observe, not at the margins, not in the fine print of secondary parameters that specialists argue over at conferences while the main picture remains intact. In the interior of the model, at the level of fundamental timelines and formation mechanisms, the kind of predictions that the model cannot quietly absorb without acknowledgement. The tension manifests in multiple ways, and it is worth listing them plainly rather than letting any single one carry the weight of the argument, because the argument is stronger when you see how many independent threads are pulling in the same direction. It manifests in the existence of TON-618 itself, a black hole of 66 billion solar masses that was already fully formed and actively feeding when the universe was less than 4 billion years old, in a state that the growth mathematics cannot comfortably produce from any plausible starting point in the available time. It manifests in the population of massive structured galaxies that the James Webb Space Telescope is finding at redshifts corresponding to the first few 100 million years of cosmic history, galaxies that contain more stellar mass than our models say the universe should have been able to assemble that quickly. It manifests in the little red dots, those compact high redshift active galactic nuclei that appear in JWST imaging in numbers and at masses that exceed what standard formation models predict for objects at those epochs. It manifests in the growth timescale calculations that fail to close regardless of how generously you set the initial conditions, regardless of how optimistically you tune the seed masses and the accretion efficiencies and the merger rates. Taken individually, each of these tensions is uncomfortable but manageable. A clever modification here, a new mechanism there, and you can perhaps address any single one of them without touching the broader framework. Taken together, consistently pointing in the same direction across independent data sets, independent research teams and independent analytical approaches, they suggest something more systemic than a local patch can fix. The phrase, "the model is incomplete," is more precise than "the model is wrong," and the distinction is not just diplomatic hedging, it matters scientifically. The lambda cold dark matter cosmological model, which is the formal name for the framework that most cosmologists work within, is not a flimsy or poorly supported theoretical structure. It has genuine, extraordinary, hard-won explanatory power across an enormous range of phenomena. It correctly predicts the large-scale structure of the universe, the way galaxies are distributed across cosmic space in a web of filaments, sheets, and voids that match what wide-field surveys actually find. It correctly predicts the statistical distribution of galaxy properties, the clustering of matter on various scales, the ratio of different types of large-scale structure. It correctly predicts the detailed pattern of temperature fluctuations in the cosmic microwave background, the faint afterglow of the Big Bang that permeates the entire sky, with a precision that required decades of increasingly sensitive instruments to measure, and that the model accounts for with remarkable accuracy. It correctly predicts the relative abundances of the light elements, hydrogen, helium, deuterium, lithium, produced in the first few minutes of cosmic history by Big Bang nucleosynthesis, a calculation that requires getting the physics of the early hot dense universe right at a level of detail that is genuinely impressive, across an enormous range of scales and epochs and observational techniques. This model works. Dismissing it would be as scientifically unjustified as ignoring the anomalies it fails to explain. What we are identifying is not a broken model, but a model with specific gaps in specific regimes. The early universe, particularly the first few billion years when the first black holes were seeding and growing, and the first galaxies were assembling their initial stellar populations, appears to be one of those regimes. The model's predictions in that regime, made using physics and parameters calibrated against observations of the later universe, appear to underestimate how quickly massive structures formed and how large they grew. The question is whether this underestimation reflects a missing ingredient that can be added within the existing framework, or whether it reflects a deeper structural issue with assumptions baked into the framework itself. That question is genuinely open, and the honest answer is that we do not yet know. The growth models for black holes, specifically, are insufficient. The mechanisms we have identified, stellar collapse producing the first seeds, gas accretion building mass over time, galaxy mergers bringing black holes together to merge and combine, are all real. They all operate. They all contribute to the black hole mass function we observe in the present universe. But they appear insufficient in the time available, given the physics we understand, to produce objects like TON-618 at the epoch at which we observe it. Something is missing from the accounting. Either the seeding mechanisms in the early universe were fundamentally different from what we assume, producing much larger initial seeds through direct collapse or primordial formation rather than through stellar evolution, or the growth rates achieved in the early universe were significantly faster than the Eddington limit, our standard ceiling on accretion rate, would suggest, perhaps through sustained super-Eddington accretion in geometric configurations that our models have not fully captured, or the cosmological timeline itself, the sequence of events and their timing in the early universe, contains an assumption that does not match reality in ways that would provide more time or more material for early structure formation than the standard accounting allows. Or, most likely and most challenging for model builders, some combination of all three operates simultaneously, and untangling their individual contributions requires observational constraints we do not yet have. We do not know which fix is correct. We do not know whether one fix is sufficient or whether multiple new ingredients are required. The honest assessment, stated plainly, is that we are looking at a system that does not close. A cosmological accounting problem in which the observed output, the masses, and formation epochs of the most extreme early black holes does not match the predicted production capacity of the known mechanisms operating within the known timeline, and we are still in the relatively early stages of understanding where exactly the discrepancy lies, how large it actually is when corrected for observational biases and selection effects, and what class of solution will ultimately resolve it. This is not a comfortable position for a mature scientific field. It is, however, an honest one. What makes this scientifically exciting, rather than simply troubling, is that this is precisely how physics has always progressed. The anomalies, the objects and observations that refuse to fit, that sit outside the boundary of the current model and resist the patches applied to bring them inside it, are not failures of the scientific enterprise. They are the most valuable things science produces because they are precise, quantitative indications of exactly where the current model ends and where the next model must begin. Every major advance in our understanding of the physical universe has been preceded by exactly this kind of tension between observation and theory, a tension that refused to dissolve, that persisted across improved measurements and refined analyses until a new framework was developed that could account for both the old successes and the new anomalies simultaneously. General relativity emerged from the failure of Newtonian gravity to account for the precession of Mercury's orbit. Quantum mechanics emerged from the failure of classical physics to account for the spectrum of blackbody radiation. The expanding universe emerged from observations that a static cosmos could not explain. The pattern is consistent. The anomaly that will not go away is the signpost pointing toward the next level of understanding. TON-618 is not just an extreme black hole. It is a data point that points outside the current framework precisely and measurably and reproducibly in a direction that other data points, the JWST galaxies, the little red dots, the failing growth curves, are also pointing. Every additional object like it that new observations reveal sharpens the direction that pointing indicates, narrowing the space of possible solutions and making the required new physics more constrained and therefore more findable. We may be seeing only a small fraction of the relevant population of early massive objects, because dust and redshift and the limits of current instruments hide many of them from us. That means the true scale of the discrepancy between model and reality may be considerably larger than current data reveals. We are not at the end of the anomaly. We may be closer to the beginning of understanding it, and that is, if you are willing to sit with the discomfort long enough for it to transform into something else, one of the most interesting places that science can be. Part Mubai, the invisible population. The objects we can observe are not a complete census of what exists. They are a biased sample, biased toward whatever happens to be bright enough, nearby enough, oriented favorably enough, or simply lucky enough in terms of the intervening material between it and us, to clear the observational thresholds of the instruments we use. This is true of all astronomy, at every wavelength and every scale, and every working astronomer knows it and accounts for it in their analyses. But it is especially relevant and especially consequential when discussing the population of early massive black holes, because in that specific context, several independent factors conspire simultaneously to hide the very objects we most need to find. The universe, in this respect, is not being cooperative. Start with dust, because dust is one of the most effective and most underappreciated obscuring agents in all of astronomy, and its effects are particularly pronounced for the kind of objects we are trying to count. Galaxies that are actively forming stars at high rates, the kind of galaxies that surrounded the most actively feeding black holes in the early universe, produce large quantities of dust as a byproduct of stellar evolution. Massive stars burn through their fuel rapidly, shed material in winds and explosions, and the heavy elements produced in their interiors are dispersed into the surrounding interstellar medium where they condense into tiny solid particles, silicates, carbonaceous grains, complex molecules, collectively called dust. This dust is extraordinarily effective at absorbing and scattering ultraviolet and optical light, the wavelengths at which most traditional astronomical surveys operate, and at which the most luminous components of active galactic nuclei emit most of their energy. A dust-enshrouded quasar, a black hole accreting at high rates and driving an accretion disk as luminous as TON-618s, surrounded by a sufficient column of obscuring dust, could in principle be entirely invisible in an optical survey, not merely faint. Invisible. The ultraviolet and optical photons that would normally betray its presence are absorbed by the dust before they can escape the host galaxy, and the dust re-radiates that absorbed energy at much longer wavelengths, in the infrared, where traditional optical telescopes are not sensitive. To detect a dust-obscured quasar, you need infrared or radio observations, and while those observational capabilities exist and are being actively deployed, they cover smaller areas of sky with greater difficulty than broad optical surveys and the characterization of a detected source. Measuring its precise distance, estimating the mass of the central black hole, determining its luminosity accurately, is substantially more difficult for an obscured source than for an unobscured one where the full spectrum is accessible. Some fraction of the early universe is actively feeding black holes, and estimates of that fraction vary widely and are themselves uncertain, are dust-enshrouded, and therefore either entirely absent from current catalogues or present only as faint, poorly characterized detections that are difficult to interpret with confidence. We do not know how large that fraction is. We cannot know without the observational tools to find them, and those tools are still being built and deployed. The orientation of a quasar relative to our line of sight introduces a related but distinct bias. The accretion disk and the surrounding structure of gas and dust are not spherically symmetric. They are flattened, with denser concentrations of obscuring material in the equatorial plane and clearer sightlines along the polar axis where the relativistic jets escape. A quasar viewed along or near its polar axis, what astronomers call a blazar or a face-on quasar, presents its brightest face to us and is readily detectable. A quasar viewed edge-on, looking through the dense equatorial dust structure, may have its central regions entirely hidden, even if the object is intrinsically as luminous as anything in the observable universe. The unified model of active galactic nuclei, the theoretical framework that describes this orientation dependence, predicts that a significant fraction of all quasars at any given epoch are obscured simply by geometry. In the early universe, where dust production was vigorous and the geometry of forming galaxies was often different from the more settled structures of the modern universe, this orientation bias may have been more severe. The redshift horizon presents a fundamentally different kind of limit, one that has nothing to do with dust or orientation, but with the physical state of the intergalactic medium itself at the epochs we are trying to probe. At very high redshifts, corresponding to the first few 100 million years of cosmic history, the universe had not yet completed a process called reionization. In the period immediately following the formation of the first stars and galaxies, the intergalactic medium, the gas filling the space between galaxies, was predominantly neutral hydrogen. Neutral hydrogen is extraordinarily efficient at absorbing ultraviolet photons, the very photons that carry the most information about hot, energetic sources like quasars. When we try to observe objects at redshifts above approximately 6, corresponding to a cosmic age of less than 900 million years, the light from those objects must pass through increasingly large columns of this neutral, or partially neutral, intergalactic hydrogen on its way to our detectors. The hydrogen absorbs the ultraviolet photons almost completely, creating what astronomers call the Gunn-Peterson trough, a near-total absorption feature in the spectra of very high redshift quasars that tells us the intergalactic medium at those epochs was still substantially neutral. The practical consequence is that looking at objects that existed before or during the epoch of reionization is observationally challenging in a way that goes beyond just needing more sensitive instruments. Some of the photons we would need to detect and characterize the most distant early black holes are simply absorbed before they reach us, converted into heat in the intergalactic medium, lost to the census permanently. Objects that existed in the first 500 million years of cosmic history, the epoch when the growth problem for objects like TON-618 is most acute and where the observational evidence most needed to test competing models would be most informative, are partially hidden behind a screen of neutral gas that even the most sensitive current instruments cannot fully penetrate. JWST, with its infrared sensitivity, can detect the redshifted optical and near-infrared light from these objects even when their ultraviolet emission is absorbed, and it has made remarkable progress in pushing observations to higher and higher redshifts. But it is working against a fundamental physical barrier, not merely an engineering one, and the information content of what it can detect through that barrier is necessarily limited compared to what a fully transparent intergalactic medium would allow. Then there is the question of luminosity thresholds. Every instrument has a detection limit, a minimum brightness below which sources simply do not produce enough signal to be distinguished from noise. The early universe black holes that have been detected, the ones that populate our catalogues and that drive the tension with the standard model, are by definition the brightest ones, the ones luminous enough to clear the detection threshold of the surveys that found them. For every TON-618, shining at 140 trillion solar luminosities and detectable across 10 billion light-years, there may be many more black holes of comparable or even greater mass that are accreting at lower rates, producing less luminosity, and falling below the detection threshold of every survey conducted so far. A dormant or low accretion ultramassive black hole in the early universe would be essentially invisible at cosmological distances. Its host galaxy might be detectable, but attributing the correct black hole mass to it without the spectroscopic signatures of active accretion is extremely difficult. TON-618, sitting at the known extreme of the confirmed black hole mass distribution, already represents a profound challenge to our models of early cosmic structure formation. But TON-618 is what we can see. It is the object that was luminous enough, oriented favorably enough, and unobscured enough to deliver its photons to our instruments across 10 billion light-years. It is the visible tip of what may be a considerably larger and more massive population of early black holes that current technology cannot access. The mismatch between what our models predict and what we observe, already significant enough to drive active theoretical debate and observational programs across multiple major facilities, could be substantially larger, possibly dramatically larger, when properly corrected for the populations hidden by dust, by orientation, by the neutral intergalactic medium, and by simple luminosity limits. We do not know how much larger. That uncertainty is itself informative, because it tells us that the boundary of the problem, the full scale of the discrepancy between cosmological prediction and early universe reality, has not yet been mapped. We are working with an incomplete sample, trying to characterize a distribution whose extreme end we may not have fully found yet. This possibility does not make the problem smaller or more tractable. It makes it potentially much larger, and it introduces a direction of future change that is worth stating plainly. As observational technology improves, as instruments become more sensitive in the infrared and radio wavelength ranges where obscured sources are detectable, as future observatories like the next generation of extremely large ground-based telescopes and proposed space observatories push detection thresholds to lower luminosities and higher redshifts, the catalogue of anomalous early massive objects will almost certainly grow. The history of astronomy at every previous sensitivity threshold has been one of finding more structure, more objects, more complexity than the preceding generation of instruments revealed. There is no particular reason to expect that pattern to reverse when we look at early black holes. Every improvement in our ability to see the early universe has sharpened the tension with the standard model rather than relieved it. We are not approaching the end of the anomaly. We are, in all probability, still near the beginning of understanding how large it actually is. And that is one of the most important open questions in all of contemporary astrophysics, precisely because it sits at the intersection of black hole physics, galaxy formation, and fundamental cosmology, three of the most active research frontiers in the field simultaneously. The answer, when it comes, will not be a small addition to what we know. It will reshape a significant part of it. Part 8, the final reframe. Let us return to where we started, because the starting point of this entire conversation was a claim embedded in a title, the suggestion that something is coming toward us, that TON-618 represents an arrival of some kind, and we have spent considerable time and travelled considerable conceptual distance to determine what that arrival actually is. We have established the scale of the object. We have walked through the physics of its formation and the mathematics of why that formation should not have been possible in the time available. We have followed the evidence from a single anomalous catalogue entry in 1957 to a systematic discrepancy revealed by the most powerful space telescope ever built, and we have established clearly that the physical object itself poses no threat of any kind. It is not approaching, it is receding. It sits 10.4 billion light-years from Earth and is being carried further from us by the expansion of space at this very moment, moving away from everything in its cosmic neighborhood, including us, the way everything at that distance moves away from everything else in an expanding universe. The title's terror, if you take it literally as a prediction of physical impact or cosmic collision, is not the real terror. It is not even in the same category as the real terror. It is a misdirection and a deliberate one, because the thing that is actually arriving is more interesting than any physical object could be. The real arrival is epistemic. That is a word that means relating to knowledge, to what we know and how we know it, and it is the right word for what is actually happening every night on those mountain peaks. The arrival is the steady, photon by photon, measurement by measurement, dataset by dataset delivery of information that challenges what we thought we knew about the universe we live in. Every night that telescopes in the northern sky collect light from the direction of Canes Venatici, every photon that completes its 10.4 billion year journey and lands on a detector is a delivery, not of matter, not of energy in any quantity that has any measurable effect on us, of evidence, of constraint, of a quiet, insistent data point that says, in the language of physics, that our model of how the universe assembled its largest structures is missing something, and that missing something is not a minor detail at the edges of an otherwise complete picture. That evidence has been accumulating since the 1970s, when TON-618 was confirmed as a quasar, and its extraordinary distance and luminosity were first properly characterized. It accumulated through decades of ground-based spectroscopy, each new spectrum adding another constraint on the object's properties. It accelerated with the launch of space observatories that could observe wavelengths blocked by Earth's atmosphere. It accelerated again, dramatically, with the first science results from JWST, which revealed not one anomalous object, but a population of them. And it will keep accelerating as the next generation of observatories come online. The extremely large telescope, currently being constructed on Cerro Armazones in the Chilean Atacama, which will have a primary mirror 39 meters across and will collect more light in an hour than previous telescopes could in a night. The Nancy Grace Roman Space Telescope, with its enormous infrared field of view that will survey the sky at depths and scales impossible for Hubble, future X-ray observatories that will characterize the hot gas around early black holes with new precision. Each of these instruments will collect its own photons from the distant early universe, and the current trajectory of discovery gives little reason to expect that more data will make the anomaly smaller. The current version of TON-618, its state in the universe as it exists at this moment, is unknown to us and unknowable with any technology that currently exists or that is currently foreseeable on any realistic horizon. The light from TON-618 as it is right now, today, this year, this century, left its source 10.4 billion years ago by definition, because that is how long light takes to cross that distance. Any signal from the current state of that object will not arrive here for 10.4 billion years. By that point, our sun will have exhausted its hydrogen fuel, expanded into a red giant, consumed the inner planets, collapsed into a white dwarf, and cooled for billions of years in the dark. Whatever exists on Earth now will not be here to receive that signal. The object we observe when we look at TON-618, the blazing hyperluminous quasar, recorded as a faint blue smudge on a photographic plate in Tonnant-Sintler in 1957, and now characterized with precision across multiple wavelengths, is a ghost in the most technically precise sense of that word. It is an image of something that existed billions of years ago, a projection of past conditions transmitted to us by the physics of light propagation through an expanding universe, received and processed by instruments built by a civilization that came into existence long after the transmission was dispatched. We are not observing TON-618. We are observing the light that TON-618 emitted 10.4 billion years ago, and the distinction is not philosophical, it is physical. The present state of that object is hidden from us behind a wall of time that no engineering or theoretical advance can penetrate. We are looking at a ghost that has not finished becoming something else, and we will never see what it becomes. What that something else might be is a matter of inference, guided carefully by what we understand about how black holes and their host galaxies evolve over cosmic timescales. Quasars do not remain quasars permanently. The process that makes a quasar luminous, the continuous infall of surrounding gas and disrupted material onto the accretion disk, depends on a fuel supply that is ultimately finite. The gas in a galaxy is a resource, and an actively feeding black hole consumes it. As the supply depletes, the accretion rate drops. As the accretion rate drops, the luminosity of the disk drops, the quasar fades. The jets that were launched by the magnetic fields of the disk weaken and eventually switch off. The brilliant point source that outshone thousands of galaxies becomes, over millions and then billions of years, increasingly quiet. The host galaxy may undergo mergers with neighboring galaxies during this period, and those mergers can deliver new gas, potentially reactivating the central black hole briefly and producing a new episode of quasar activity, what astronomers call an AGN flicker. But these reactivation events are typically shorter and less luminous than the original quasar phase, and over cosmic time the general trajectory is toward quiescence. The most massive black holes in the present-day universe, the ultramassive objects sitting at the centers of giant elliptical galaxies in the cores of massive galaxy clusters, are thought to be the descendants of the most luminous quasars of the early universe, now dormant or nearly so, their fuel exhausted, their accretion disks depleted, their jets quenched. TON-618, if it follows this general evolutionary trajectory, which we have every reason to expect it does, may today be precisely such an object. A dormant, ultramassive black hole, 66 billion solar masses of compressed spacetime sitting at the center of a massive elliptical galaxy, accreting at a tiny fraction of its peak rate, producing little luminosity, invisible to surveys that would have easily detected it in its quasar youth. We cannot confirm this. We cannot see it. The photons that carry information about its current state will not arrive for an unimaginable length of time. All we have is the ancient transmission, still arriving, still delivering its payload of observational challenge, still demanding an explanation. There is something in that situation that I find genuinely moving, and I want to be honest about that, rather than just treating it as a rhetorical flourish at the end of a long discussion. We have built instruments of extraordinary precision, optical systems assembled to tolerances measured in nanometers, detector arrays cooled to temperatures near absolute zero to reduce their own thermal noise, all of it carried into space, on rockets, or installed on mountaintops accessible only by winding roads at altitudes where the air is too thin to breathe comfortably for long. We have trained generations of scientists and engineers to design, build, operate, and interpret the outputs of these instruments. We have developed mathematical frameworks of remarkable sophistication, drawing on general relativity, quantum mechanics, thermodynamics, plasma physics, and computational methods to extract physical meaning from the signals those instruments collect. And what all of that accumulated human effort reveals, when it peers back far enough into the universe's history, is not confirmation. It is the boundary of what we know, mapped precisely by the place where the data stops agreeing with the predictions. Not a reassurance that the universe behaves the way we expected, a demonstration that it does not entirely, not in the regime that matters most for understanding how the first and largest structures assembled themselves. The universe is not required to fit our models. The models are required to fit the universe, and when they do not, the universe wins every time, without negotiation or exception, and we go back to the equations. The message from TON-618 is not a warning. It is not a harbinger of disaster. It is not even, really, a mystery in the dramatic sense that word usually implies. It is something at once more mundane and more profound than any of those framings. It is a 10-billion-year-old experimental result that our current best theories have not yet fully passed. Every photon from that object that lands on a telescope mirror is a test of our models. The test keeps running every clear night. The test keeps arriving on schedule, and the models keep failing it in the same quiet, specific, reproducible way. The black hole is there. It is that large. It existed that early, and we still cannot fully and satisfyingly explain why. That is not a crisis. That is science doing exactly what science is supposed to do, which is to keep testing until the tests reveal where the understanding breaks down, and then figure out what comes next. How many objects like TON-618 exist beyond our current observational horizon, hidden by dust or neutral hydrogen or simple distance? How many ultramassive early black holes are sitting in the early universe at redshifts our instruments cannot yet reach? Their photons still traveling toward us but not yet arrived, their existence unknown to us and unknowable until the technology catches up. How much worse does the mismatch between what the standard model predicts and what the universe actually produced get when we can finally see those objects? The answer, given the direction of every observational advance made so far, is almost certainly that it gets worse before it gets better. Every new telescope has revealed more objects that should not exist by the prior reckoning. Every increase in sensitivity has found the anomalous population to be larger and earlier than the previous instrument revealed. There is a version of this story that ends with a genuine revolution in cosmology, a reconstruction of our understanding of early universe physics so thorough that the textbooks describing cosmic history look meaningfully different in 50 years. There is another version where the anomalies are resolved within the existing framework by adding new mechanisms, direct collapse, primordial seeds, super Eddington growth phases, none of which require breaking the model, only extending it. There is a third version where future measurements tighten the constraints in ways that bring the observations and predictions back into agreement, revealing that current tensions were partly artifacts of incomplete data. Scientists in this field disagree, genuinely and productively, about which version is most likely. That disagreement is not weakness. It is the normal and healthy state of a field actively confronting real evidence with real stakes. What is not in dispute is that TON-618 exists, that it is what the measurements say it is, that it was there when the universe was young and our models were not expecting it, and that the search for a complete explanation of how it came to be is one of the most consequential open problems in contemporary astrophysics. The light from it is not stopping. It will keep arriving on those mirrors, keep becoming data, keep demanding from the equations an answer they have not yet fully provided, and somewhere in the continuing analysis of those photons, in the next generation of instruments, and the theoretical frameworks not yet written, in the work of researchers who may not yet be in graduate school, the answer is being assembled, slowly, by accumulation and challenge and revision, the way every real understanding of the universe has ever been assembled. The early universe was stranger than we imagined, more energetic, more productive of extremity, more willing to build things that violated our expectations of what the available time and physics should allow. And the objects it built in that early, strange, productive period are still out there, still emitting the ancient light of their youth into an expanding universe, still sending their transmissions toward instruments that may not exist yet, carrying messages about physics we have not yet learned to read correctly. TON-618 is one of those transmissions. It left before we existed. It arrived while we were still figuring out how to listen. And it will keep arriving, photon by patient photon, until we finally understand what it is telling us. We are younger than the light we are seeing. The light is still talking. And the question it keeps asking, the one encoded in every photon that lands on every mirror, on every mountaintop tonight, is simple and unanswered, and one of the most important questions in science. How did something this large exist this early? And what does its existence tell us about a universe we thought we understood?